class. So today we will learn on chapter 2 for the bonding of organic ligand to metal. For the introduction, firstly you have to know the definition of the olefin complex. Olefin is referring to the hydrocarbon containing a carbon-carbon double bond, also known as alkene or ethylene. And the definition of the pi donor ligand is any compound or ligand that can donate electron from a filled pi orbitals of the ligand to the metal. And a ligand is any molecule or ion that has a lone pair of electron to be donated to a metal center to form a coordination compound. And ligand can be said as a Lewis base, meanwhile for the metal center is a Lewis acid. Lewis base means that it's a donate electron. Meanwhile, for the Lewis acid means it accept electron. The presence of the lone pairs of electron can be seen easily in the case of the previously discussed CO molecule, a common ligand that has a Lewis electron dot structure as shown below. So we have here a carbonyl structure, and this one is the C2H4 molecule. However, no lone pair of electron exists in the ethene compound, but yet it can also behave like a ligand. Ligand is actually any species that are electron rich like an ethane molecule. So we have, if we look here, the carbonyl ligand, CO ligand consists of contain the electron which can make a bonding with the metal center through the lone pair. But ethene is also an electron rich compound, so it can behave as a ligand also. Ethene can behave as a ligand by donating its pi electron to the metal Lewis acid instead of the traditional lone pair of electron, such as carbonyl. Hence, olefin are said to be an ideal pi donor ligand if it can accept electron from the metal into pi star ligand orbital. It is also a pi acceptor or pi acid ligand. Okay, so we have example here for the olefin complex where we have a metal center bonded with the ethene. The example is this salt. So this salt is the first organometallic compound synthesized in 1827, and it is called an olefin compound. It can be obtained by reaction of the KCl, PtCl2 in the ethanol. And we have the molecular structure of the zinc salt is KPtCl3 C2H4 H2O. Okay, so this is the molecular structure and this one is the molecular formula. So we have K is the counter ion and this one is the coordination complex. So this coordination complex consists of a Pt as a metal and then ethene as a ligand. And we have 3 Cl atom bonded to the metal center. So ethylene was shown to be approximately perpendicular to the PtCl3 plane with the H band away from the metal. Okay, we have a mechanism of Dua-Chet-Duquesne model for the bonding of ethene or we call ethylene to a metal. So we have here if we look at the previous topic on the chapter 1, we have the synergistic bonding mechanism between the metal with the carbonyl. So we have a sigma bonding from the ligand of the carbonyl to the metal center first, and then we have a pi back donation from the metal to the carbonyl. Same goes to the ethylene when it bounds to the metal center. So we have here the first type of bonding is sigma bonding, where the ethene ligand will donate its electron to the metal center. And then next, to stabilize the electron at the metal center, so the metal will tend to give back its electron to the ethene. So this mechanism is called as a Dua-Chet-Duquesne model. Okay, so we also have sigma bonding and pi back donation. So if the question asks you to draw the mechanism of Dua, so you need to draw these two mechanism. So you can only draw only one So it will be not complete. So you need to draw both for the sigma bonding and pi back bonding. So like this one lah. Okay, the model suggests a synergistic bonding mechanism. The first one, we have donation of electron from the 18cc pi electron from the HOMO to the empty metal orbitals of the metal. And then we have the pi back donation from the field metal hybrid orbital to the pi star orbital or LUMO on the 18. Okay, the most stable olefin complex are found with metal in low oxidation states such as Ag1, copper 1, and iron 0 as shown in the complex in the example below. So we have here metacarbonyl of the iron, and then we have cyclooctadiene. Okay, this cyclooctadiene act as a ligand and it will bond with the metal of the iron. So ethene or ethylene having only one double bond is a 2-electron donor ligand like CO. In a polyalkene, each double bond which bind to the metal center act as a 2-electron donor. So we have the cyclooctadiene of the COD, or we call it as a COD. The number of electron it carries will be 4 because we have here 2 double bond. So if we have a ligand with a 3 double bond, so we can say that the electron that it carries will be 6. Okay. So next one, the definition of the hapticity. So hapticity is the number of atoms in the ligand which are directly coordinate to the metal, and it is derived from the Greek haptin, which means to fasten. And it has a Greek symbol, eta, which is read as hapto. And hepta, and nomenclature, where n is the number of atoms bonded to the metal center. Okay, so we count the number of atoms bonded to the metal center and we will represent it by using the n superscript. And n is not always a fixed number because many ligands can bind in more than one way to a metal center. For example, we have a cyclooctatetraene. Okay. So untuk for the next one, hepto 3C3H5, we read it as a trihaptoallyl. And hepto 5C5H5, we read it as a pentaheptocyclopentadienyl. So we read the prefix first. For example, here we have 3, so it will be tri, and we read the hapto. Tri, hapto, and the name of the ligand. For this one, penta, because the number of hapticity is 5, so pentahapto cyclopentadienyl is the name of the ligand. Okay, in the structural formula, the totality of the pi bond usually is represented by a single line instead of an arrow from each bond. So instead of we write or we draw like this one, we just need to draw a straight line like this one. So the assumption is that the hapticity is the needed to satisfy the 18 electron rule. Okay, so this is the way on how we can draw the hexa, hepto, C6, H6. Okay.